Hello, everyone. Welcome to our webinar. My name is Justin D'Souza. I'm a quantitative specialist here at Statistics Solutions. During today's webinar, we are going to look at regression models, how to set them up, what types of variables you need to run them, and we'll go through a demonstration in SPSS as well. My colleague Sierra is going to put some hyperlinks in the chat box for scheduling consultations and checking out our website resources. If you have any questions, you can type them into the chat box, and at the end of the session today, we will do a Q&A, a question and answer session. So just let us know if you have any questions. We'll dive in, and we'll send everyone a copy of the recording and the PowerPoint itself. All right, so first we'll give a brief overview of the services we provide at our company. Then we'll explore what types of regressions you can run. We'll look at a demonstration in SPSS, and then we'll conclude with a summary and a Q&A session. On this slide, you can see all the various parts of the dissertation journey that we assist with, starting with topic development and going all the way to final defense. So if you've hit a roadblock at any point in the dissertation journey, or maybe you're working on a thesis or a journal publication, we can help expedite the process and help you address committee feedback. We can even crunch your numbers for you. If you just send us your data set and your template for your school, we can crunch the numbers in SPSS and present an APA write-up for you. Even developing research questions and figuring out what is the minimum sample size I need to target. We have statisticians, we have qualitative specialists, and we have literature review specialists. If you have questions about the services, you can give us a call for free at 727-442-4290. All right, so we're looking at regression models today. I think it's important to lay the foundation for what types of variables you can have. If you understand the differences between continuous, nominal, and ordinal, then you can determine what type of regression you need to run. So continuous variables are variables that fall on a continuum. They're also called interval, ratio, or scale. They all kind of fall into the same family of continuous. So examples of these are test scores, temperature in Fahrenheit or Celsius, weight, BMI, or composite scores from a previously validated instrument. So if you have individual Likert scale data, like strongly agree to strongly disagree, once you take an average or a sum of those Likert scale items to build a new variable, that resulting variable is considered continuous. So if you have decimals or numbers as options, that's usually continuous. Nominal variables are categorical factors. So you need to have two or more distinct categories, but there's no intrinsic order to these categories. So there's no hierarchy or ranking. So examples like this are gender, ethnicity, or passing and failing of an exam. We have distinct categories within each of these variables. Ordinal variable is a subset of a nominal variable. However, this does have a natural progression. There's a natural ordering or ranking. So examples of this would be education level, or a single item on a Likert scale on a survey. So strongly agree to strongly disagree, a 1 to 5 or a 1 to 7 scale. That would be an ordinal variable. Okay, so with that understanding, if you are trying to predict an outcome, that's usually when you run regression models. Prediction is the key word there. So if you're doing a linear regression, that means you are trying to predict a continuous outcome. Okay, so you need to have a continuous dependent variable to run a linear regression. On a binary logistic regression, you need to have an outcome that is binary or dichotomous. So a variable like passing and failing of an exam, if that was your outcome or your dependent variable, then you can run a binary logistic regression. A multinomial logistic regression is just a regression that has 3 or more categories. So instead of pass or fail, if you had a third category there, pass, fail, and a third grouping. Then you could do a multinomial logistic regression. And then an ordinal logistic regression is used when you're predicting an ordinal outcome. So if you're predicting a single Likert scale question, or if you were predicting education level, and you can run an ordinal logistic. Okay, and just to get familiar with the terminology, across multiple studies, you can use independent and dependent variable. You'll probably see that fairly often, but synonyms for that when you're doing regressions, an independent variable is considered a predictor, and a dependent variable or the outcome is considered the criterion. Okay, in regards to the predictors, so what you're putting into the regression model to predict your outcome, your predictors can be any level of measurement, but you have to code them in a certain way. So you can have continuous, nominal, and ordinal predictors. And in terms of the coding, if you have a continuous predictor, so just a variable that is numeric that you're putting into the model, you don't need to make any adjustments. For the coding, the variable is put in its natural format. You don't make any changes. However, if you have a dichotomous predictor, such as passing and failing, typically you would code the absence of a condition as the lower value. So if it was pass, fail, fail would be a 0, 1 would be a pass. Or if you have yes, no items that you're including, yes would be a 1, no would typically be a 0. Now, if you have nominal variables that have 3 or more categories, for example, ethnicity, you have to follow a process called dummy coding. The dummy coding is going to create multiple variables within your variable, but you need to pick one of those categories to be a reference. So this is a semi-complex topic if you're not familiar with it, but if you just Google or go on YouTube and search for dummy coding, it will explain the process. The idea behind this is that a regression model doesn't know what these numbers mean. It doesn't know that 1 is white, 2 is black. It doesn't understand that underlying meaning. So the way we assign meaning to that is by dummy coding. So you pick one reference category. If you're looking at ethnicity, it's often the white category because that tends to be the most prevalent in surveys. But what you would do is you would create 4 dummy coded variables. You would have black versus white, Asian versus white, Hispanic versus white, and other. All right, then you want to verify the statistical assumptions of the regressions. So we'll look a little bit more at that. Linear regressions have more strict assumptions to check in comparison to logistic regressions. So the most common assumptions I see are checking for normality of the residuals, checking for homoscedasticity, and absence of multilinearity. We'll look at some examples for that. Okay, so let's look at an example here. I have a sample data set that contains different car models. Each row is a different car model. Camaro, we have Pontiac, we have a Honda Civic in here. So the rows are individual cars. The columns are variables of interest, such as the mileage, what is the weight of the car, what is the quarter mile time, what transmission type does it use, automatic or manual. So let's develop a hypothetical research question. So let's say, does horsepower and the weight of the car predict the mileage? The mileage is our outcome. This is a continuous variable because it's numeric. We have decimals as possibilities. So I would run a linear regression here. We'll go to analyze, regression, and linear. And then for the dependent variable, that is going to be the outcome. We'll put mileage up there. And then let's put in heat and horsepower. That. And for assumption checking, okay, so assumptions are built into the regression menu here. So what you need to do is go to plots, and we'll check mark this option right here, normal probability plot. Then we'll put in Z predictor here, and Z residual here, that is going to generate a homoscedasticity plot, so a residual scatter plot. Continue. Then we'll go to statistics. And we're going to check mark this option right here, collinearity diagnostics. That is going to check for absence of multicollinearity. Click continue and OK. Right, and then this is the output that is generated. So let's come back to the PowerPoint here. There are 3 steps you should follow when interpreting a regression. So first, you want to look at the omnibus test. What the omnibus test is telling you is collectively, do we have a significant regression model? So for this, you need to look for the p-value, and the p-value needs to be less than 0.0. You identify significance. Okay, so let's look at the output here. First, we'll look at assumptions. Okay, so if you scroll to the very bottom of this, you'll see the normal probability plot and normal PP plot. And ideally, you want your data, which is these little blue circles, you want it to follow this diagonal trend line. The diagonal trend represents perfect normality. So in this case, we do meet the normality assumption. The second assumption is homoscedasticity. So we're looking at this plot here, and all you want to see in this one is random scatter, random spread, showing independence of the responses. So we don't see like a straight line. We don't see an exponential curve. It looks fairly scattered here. So that assumption is supported. And then the third assumption is absence of multicollinearity. And you can see that is tested right here. We're going to look at EIF values. So those are called variance inflation factors. And absence of multicollinearity is making sure that your predictors are not highly related to one another. So in this case, horsepower and weight. The VIFs are evaluating what is the association between horsepower and weight. And when you run a regression, you don't want your predictors to be highly associated with one another. You want them to be fairly independent. So to check for this, we look at the VIFs, and these values need to be below 10, ideally, which they are. So that assumption is met. Now, in terms of the interpretation, so the first thing you do is you look at the F-test, and the F-test is in this box right here. We see 69.21. That number is not interpretable on its own. You need to look at the next column. Next column has the p-value or the significance level, and the p-value is significant here. It's below 0.05. So what that means is collectively, both horsepower and weight in conjunction appear to predict miles per gallon. And then another thing you can interpret is right here. So the R squared value. So the 0.827, if you convert that to a percentage, that's 82.7% of the variance or the change in mileage can be explained by horsepower and weight. And so that was step 2, look at the R squared. And then step 3 is interpret each predictor on its own. However, you only do this step if you have a significant F-test. You only go to step 3 if step 1 provided a significant result. Okay, as it did in our example, we have a significant F-test. We can look at each predictor and evaluate the strength with a t-test. You see the t-test findings are right here. Here's the t-test in the coefficients table. And we look at the p-value for each of those. Horsepower, the p-value is 0.001, and weight, the p-value is less than 0.001. We do have evidence of a significant predictive relationship between horsepower and weight on mileage. Now, what is the directionality and the magnitude of those relationships? You look at the unstandardized beta column right here. And for horsepower, what this indicates is that as horsepower increases, the mileage tends to decrease. We have a negative coefficient right there. And likewise with weight, as the weight of the car increases, the mileage tends to decrease. That with a negative sign again. Okay, so that's pretty much all the steps you interpret. F-test, the R squared. If the F-test is significant, then you interpret each predictor on its own. If it's not significant, you just stop right there. Don't go to step. All right, so that is a linear regression. For a example for a binary logistic regression, we need to have a dichotomous or a binary outcome. And I'll just use this one as an example, transmission type. So we have an automatic and a manual transmission. For SPSS and a lot of softwares, you need to recode that into numbers, as I've done here. So transmission type 1 represents automatic, 2 represents manual. So we'll do a similar regression with this. We'll go to analyze regression, but instead of a linear, we're going to do a binary logistic. Binary just meaning that our outcome has 2 possibilities, automatic and manual. So then this menu will pop up and we'll put in transmission type at the very top here. And we'll just keep it simple. Let's just put in horsepower for this example. And there are no, for logistic regressions, there are not strict assumptions to check. So you don't really need to dive into the menus here. The default settings should be sufficient in SPSS. So the interpretation for this is very similar. For a logistic regression, instead of the F-test, we're going to look at the chi-square test for the collective model fit. And that result is right here, omnibus test. And we see 2.00 is the chi-square value. The p-value associated is 0.157. So that p-value is greater than 0.05. So we don't have a significant regression model here. And the next component you can interpret is the coefficient of determination. You can use the McFadden's R squared, or you can use a Nagel-Kirke R squared when you do a logistic regression. So in this case, for SPSS, they provide a Nagel-Kirke R squared. So that's about 8.2%. You change it to a percent again, 8.2% of the variance in our outcome is transmission type. So 8.2% of the variance in transmission can be explained by horsepower. And because we don't have a significant model in step 1, we actually don't even need to go to step 3. But as we can see, looking at the variables in the equation right here, and you go across horsepower, horsepower does not have a significant p-value. So regardless, if you decided to stop after step 1, or if you go on to step 3, we can see that horsepower is not a significant predictor. So that's the interpretation. Horsepower does not significantly predict transmission type. Okay, so in summary, this is primarily used when you're trying to predict an outcome. So prediction is the key word here. And that should be in your research question and your hypotheses. You know, does your independent variable predict here? And then you can figure out what is the best regression type to run, and that is contingent on what level of measurement you're looking at. So continuous, if your outcome's continuous, linear regression. If it's nominal, logistic regression. And if it's ordinal, you do an ordinal logistic. It's kind of a rare situation. I don't see that run very often. And then you need to check if your assumptions are met. So as I showed, that is built into the regression menu and SPSS. Follow the 3 steps for interpretation. You look at your omnibus test, you look at your R squared value, and then you interpret each predictor on its own. And then you can use SPSS or SAS or Stata to crunch the numbers and present your findings. So if we have any questions, you can type them into the chat box. I do see we have a question from Mahi. Will we receive the recordings after the workshop? Yes, you will receive the PowerPoint and the Zoom recording. Okay. If you have any questions about regressions, you can type those in. Is it easy to learn SPSS after learning SAS? I actually don't know how to use SAS. I haven't learned how to use SAS. I've learned Stata, R, and SPSS, so I can't definitively say. But I think SPSS is very intuitive. Once you understand where all the menus are, it comes very secondhand nature. I use SPSS every day, so I would strongly recommend SPSS. It can be a little expensive, but if you are a student at a school and you have a .edu address, email address, then you should be able to get a discount. But yes, SPSS is very intuitive. Okay, do we have any other questions? Case, I did see some people joined a little late. These are all the different parts of the dissertation that we assist with. If you have hit a roadblock, just let us know. You can give us a call, or you can use the link that Sierra provided to schedule a meeting. Thanks for joining, Isa. All right. Well, have a great day, everyone. Come join us for future webinars and let us know if you have any questions. Take care.